Time is vast, and yet in our brief candle flicker of existence, we forge civilizations that seek to outlast the stars themselves, and map the ages to come. We live in a moment, a flash of thought and breath, amid a universe whose lifetime defies comprehension. The cosmos did not begin with stars or galaxies, but with a blinding surge of energy and symmetry broken in an instant, setting into motion a chain of epochs that span from the tiniest fraction of a second to ages far longer than the current age of the universe itself. Some of these epochs are so brief they slip through our fingers like grains of sand. Others stretch into eons that could swallow the entirety of recorded history a billion times over and still be young. The stars, so eternal to us, are but a chapter, perhaps not even that, in the larger chronicle of time. And through it all, the great question lingers: can civilizations endure through these epochs? Will we simply fade like starlight, or find new ways to shine, long after the stars are gone? Can life, thought, and purpose outlast the death of stars and the dissolution of matter? Could it even have existed before they did? Today, we'll begin a journey not just across space, but through the very eras of time itself, mapping out the cosmic calendar from the first quantum flickers of existence to the last twilight of the universe, perhaps even beyond, and asking what kind of civilizations might rise and fall across this timeline. Of course, before we begin counting down the birth and death of everything, now is a good time to pause the cosmic clock and do something truly eternal. Smash that like button and subscribe. Unlike stars, which burn out, or protons, which might decay after 10 to the 40th years or so, your support helps keep this channel running right up to the end of time, or at least next Thursday. Now, with that plug out of the way and entropy satisfied, let's start mapping the great calendar of the cosmos, one tick at a time, and introduce a scale that can actually keep up, the T-scale, our logarithmic timeline for making sense of eternity. The T-scale, time, terrifyingly large and small. When dealing with the history of the universe, one quickly runs into a problem. The numbers get absurd, fast. It's not just millions or billions. Cosmic history spans everything from billions of a second to googles of years, and trying to keep those straight using plain numbers is like trying to describe the ocean or a molecule of water using a shot glass. On this show, we often discuss periods of time where even trillions of years is an eye blink, and so we use a formalized logarithmic timescale meant to make it easier to reference, which we call the T-scale, where time is written as 10 to the T power years. So T0 equals 1 year, T1 10 to the 1 or 10 years, T2 is 10 to the 2 or 100 years, and each step up or down is multiplied or divided by 10. So T3 is 1000 years, T9 is a billion years, T100 is 10 to the 100 years, and so on. To capture the earliest moments after the Big Bang, we count down the T-scale into negative numbers. T-1 is 0.1 years, T-2 about 4 days, T-6 is roughly 30 seconds. The Planck time, the smallest meaningful unit of time, 1.7 times 10 to the negative 51 years, corresponds to T-51. It marks the beginning of time as we understand it, a moment when space and time were so compressed and chaotic that quantum effects dominated, and the very concept of before loses its meaning. So T-51 to T-50 take us into the Planck epoch, the first tickings of the cosmic clock. After several million of those comes the grand Unification Epoch, around T-43, which we'll begin with shortly. Though these sub-second epochs aren't the main focus of today's episode, they are important stepping stones. The next is the Inflationary Epoch, likely ending around T-39, followed by several more rapid transitions, culminating in the Hadron Epoch, our first that actually lasts several full seconds rather than mere fractions of one. These early moments, faster than a hummingbird's sneeze, contain the most rapid and dramatic changes in the entire history of the universe. Forces split, inflation expands the cosmos at ludicrous speeds, and fundamental particles crystallize out of the quantum chaos. But don't focus too much on how short these epochs were by the clock, because what matters more is the density of events happening within them. The black hole era may stretch on for trillions of years, but it likely contains fewer events than many of these brief primordial epochs, and even fewer than our own time. Back then, particles were interacting at a frenetic pace. While very unlikely in our universe, under slightly different conditions, it is conceivable that life and intelligence might have arisen even during such early eras. From an intelligence standpoint, a being that thinks a billion times faster than us could experience a rich full lifetime in just a few seconds, during the T-7 or T-6 timelines, like the Hadron Epoch. Conversely, a mind existing in a distant black hole era, running trillions of times slower, might still experience untold eons of subjective time long before that era even begins, 10 to around T67 or so, 10 million, trillion, 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 trillion years from now. Our own era is the T10 era, being around 10 billion years after the Big Bang, about the time life appeared on Earth. Most galaxies and stars, including our Sun, formed during T9, which spans from 1 to 10 billion years after the Big Bang. The T10 era will run from shortly after Earth's formation until about 100 billion years after the Big Bang, well before the Sun's natural death, though its white dwarf remnant will still be glowing by then. And we do have some tricks for extending our Sun's life. It is unlikely that intelligent life arose before the T10 era, though we'll revisit that topic. Life emerging in the late T9 is not terribly improbable. Indeed, Earth was over 700 million years old at the beginning of the T10 era. And while life and intelligence in earlier eras are extremely unlikely under our current understanding, they cannot be entirely ruled out. Still, T10 and beyond is our primary focus today, especially for intelligence. And while this episode fits nicely into our Civilizations at the End of Time playlist, it is not truly part of that series. We're not focusing on how civilization might survive in a particular cosmic endgame, but rather on how time itself unfolds in the grand cosmic calendar. 2 words of caution. First, the T-scale is arbitrary and round. I made it up, as we use base 10 and decimal, but there's nothing special about 10 billion to 100 billion years, the official T10 era, beyond that it's convenient for us. Whereas we could have set an Earth epoch that lasts from 9.3 billion years after Big Bang to 19 or 20 billion years after Big Bang, when our red giant sun would crisp Earth. So the T-scale is just a scale for convenience. Second, each step on the T-scale is 10-fold increase in duration, and this can cause a kind of mental flattening of time. Logarithmic scales often have this problem. It's understandable, the human brain simply isn't wired for these scales, but to give perspective, the black hole epoch, spanning from T67 to T100, while only 33 steps, will last a billion, trillion, trillion times longer than all the time that came before it, and the time before that epoch even begins. That's a billion, trillion, 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 trillion times longer than the universe has existed so far. So the next time someone says, that will take forever, you now have a scale to check just how serious they are. Now, let's consider some epochs that took almost the exact opposite of forever, and yet were very busy and important periods indeed. The Grand Unification Epoch. We are not sure what, if anything significant, was going on after the infinitesimal Planck epoch, but once gravity peeled off as its own force, the remaining 3, electromagnetism, the weak nuclear force, and the strong nuclear force, were likely still unified. This grand unified epoch lasted until temperatures cooled to around 10 to the 29 Kelvin, at which point the strong force broke symmetry and became distinct. So what the heck does that actually mean? In physics, symmetry breaking doesn't mean something shattered. It means the laws that once treated all forces the same began to act differently. Think of a pool of water that freezes. While liquid water has the same properties in all directions, due to the random motion of molecules that averages things out, once ice forms, the molecules get stuck, and certain directions in the ice crystal become special. The symmetry got broken. Same, a ball resting on a smooth and symmetric hill, given a tiny push one way or another, falls in one direction and breaks the symmetry immensely, even if it was Brownian motion that shoved it to one side. Similarly, as the universe cooled, the once identical behaviors of the fundamental forces diverged. The strong force, which binds quarks together into protons and neutrons, took on a unique identity and stopped behaving like the others. This shift may have unleashed cosmic inflation, the ultra-rapid expansion of space that follows. It is also the era that might have produced exotic relics like magnetic monopoles, hypothetical particles that carry a single magnetic charge, north without south or vice versa, and which many grand unification theories predict should exist, though none have yet been found. It may also have left behind topological defects, strange discontinuities in spacetime like cosmic strings or domain walls, much like cracks in ice as water freezes, and perhaps most importantly, it may have created the matter-antimatter asymmetry, a tiny imbalance in laws of physics that caused slightly more matter than antimatter to form, letting the universe avoid self-annihilation and giving us a cosmos made of something rather than nothing. The Inflationary Epoch. Inflation is when the universe hit the cosmic accelerator, expanding faster than the speed of light, not because objects were moving through space, but because space itself was stretching exponentially. This does not violate relativity in any way. In fact, most of the observable universe is currently receding from us faster than light, precisely because space is still expanding, and over very large distances, that expansion exceeds light speed. But the inflation epoch really happened. There was a brief moment, lasting just trillions of trillions of trillions of a second, when that expansion was extremely intense, ballooning the universe from subatomic scale to perhaps the size of a grapefruit or a basketball, or maybe a bit larger. It also cooled sharply. Normally when working with an ideal gas, which was more or less the case here, if you double the volume of something you half its temperature. Since volume rises with the cube of distance, if you make something 10 times wider, its volume will drop by 1,000, and its temperature drop to 1,000th. Low-end estimates for inflation would be 26 orders of magnitude, 100 trillion times wider, or 78 orders of magnitude of volume. So by simple approximation, you'd expect the temperature to drop 78 orders of magnitude or more. I should also note two important caveats. First, inflation is still entirely theoretical. We do not know what caused it, even if it happened, only that it explains several otherwise puzzling features of the universe. One key piece of evidence is the observed smoothness of the universe on large scales, yet the presence of structures like galaxies and superclusters on smaller ones. That wouldn't be expected if everything expanded evenly from the Big Bang without some process like inflation. Second, despite the extreme density during this period, there actually weren't many interactions happening. That's because all force-carrying particles, gravitons, photons, and the rest, move at or below the speed of light. And during inflation, everything was expanding away from everything else faster than that. In effect, causality was broken on small scales. It is also worth noting that when we say the universe went from subatomic to basketball-sized in an instant, we are referring to the observable universe. The entire universe beyond our cosmic horizon, the bits expanding away from us faster than light, may have already been much larger than that and expanded even more dramatically. Some versions of multiverse theory suggest inflation never actually stopped on those larger scales. And yes, infinity can grow. It is not a number, and infinity plus infinity can be larger than either starting infinity on its own. I want to spend a bit more time on this epoch because in my experience, science videos tend to go one of two ways. They either simplify inflation down to the universe expanded from the size of an atom to a basketball in an instant, or they leap straight into advanced physics that 99.99% of people cannot follow. There's not much middle ground, no pause to mention that we're really only talking about the observable universe, or that inflation may have expanded things so fast that no particle could interact with its neighbors, because even light couldn't keep up, or that the main reason we think inflation happened at all is because of how the universe looks today, smooth and flat on large scales, but lumpy on smaller ones. That pattern suggests it did not start that way. Those irregularities had to come from somewhere, and inflation neatly explains how tiny quantum fluctuations could get stretched out to see the structure we see now in galaxies, clusters, and cosmic webs. Now, why do those exist at all? Quantum events are constantly popping in and out of existence, like tiny sparks of energy flicking across the fabric of reality. For those who remember TV static, every pixel randomly flashing black and white, that's a decent analogy for what happens at the tiniest scales of the universe. If you freeze frame that screen and then blew it up to the size of a football field, you'd see big, uneven patches of black and white, still random, but now large enough to stand out. That's a bit oversimplified, but it will do. The idea is that tiny quantum fluctuations, brief random variations in energy at subatomic scales, were stretched out by inflation into macroscopic ripples. These ripples became the seeds of all galaxies and cosmic structure, like fingerprints stamped across the cosmos. What began as momentary blips in the quantum foam were ballooned by the rapid expansion, locking in density differences that gravity would later amplify, eventually forming stars, galaxies, and everything else we see when we look up at the night sky. Because of this, on galactic scales and below, the universe isn't smooth at all. It looks more like a vast spiderweb, or even the tangled firing of neurons in a brain. And I mention that because this is your first moment where intelligence could be considered possible. Not plausibly in our universe, but with the right physical constant and expansion rates, you could have gotten a randomly assembled brain, a Boltzmann brain, even at this early epoch. Before this moment, no, again inflation was superluminal, so no activity between particles, and thus hypothetical neurons would be impossible. This could have happened for us too, except a moment later things got ultra hot again. The Electroweak Epoch. So inflation has ended and the universe reheated to enormous temperatures, both from thermalization of all those particles interacting again, now that expansion no longer travels faster than interactions, and from inflation field decay, the details and mechanisms of which are still rather debated. We get a reheating phase that returns us to the very hot Big Bang state after cosmic inflation cooled it. Now things are very hot, and so weak electromagnetic forces remain unified for a while longer. Trillions upon trillions of Planck-time cosmic clock ticks will need to pass, but the universe is still expanding, albeit much slower, and cooling as it goes, so around T-19, a trillionth of a second after the Big Bang. Those two forces decoupled, and the four fundamental forces we know today finally stood distinct: gravity, the strong nuclear force, which again decoupled before inflation, and now the weak nuclear force and electromagnetic force. This epoch includes many high-energy particle interactions and sets the stage for matter as we know it, as everything is banging around together at temperatures and densities that make the core of a star-going supernova look cool and thin. It is also during this era that the Higgs field is thought to have condensed and given mass to particles via the Higgs mechanism, a crucial step in producing the stuff stars, planets, and people are made of. Before this, there was no mass, and this is important because the transfer particles for the weak nuclear force, the W and Z bosons, are vastly more massive than the particles they are usually moving between, like using a life-size bus to ferry people between two dollhouses. The W boson, for instance, is 86 times more massive than a proton, and tens of thousands of times more massive than an up or down quark. Until the Higgs field condensed and allowed mass, none of these particles would have acted as they do now, and that includes electrons and quarks, which have mass. Speaking of quarks, the Quark Epoch. Now that we have mass and four distinct forces, the universe can be classified as a dense, hot plasma soup of quarks, anti-quarks, and gluons, all constantly colliding and transforming. It was too hot for quarks to bind together into protons or neutrons yet. Matter and antimatter were still mostly annihilating each other, but due to some tiny asymmetry, perhaps just 1 part in a billion, matter eventually won out. This imbalance ensured a residue of matter would survive, instead of everything annihilating in light. Not that antimatter collisions always result in photons anyway, especially at very high energies. The Hadron Epoch. Around a second after the Big Bang, temperatures dropped to around 1 trillion Kelvin, and quarks cooled enough to bind into hadrons, particles like protons and neutrons held together by the strong nuclear force. This epoch marks the beginning of the transition from a particle-dominated universe to one built from atomic matter. Antimatter was still present and annihilating with matter, but by the end of this era, nearly all of it was gone, leaving behind a small surplus of hadrons that would eventually form atoms, stars, galaxies, and us. Conditions were still hotter than the core of any modern star, and fusion reactions were underway. In just a few minutes, the vast majority of the universe's hydrogen, helium, and a trace of lithium nuclei were forged. The rate of new element formation then began dropping off sharply as the universe expanded and cooled. Had expansion proceeded a bit more slowly, heavier elements might have formed right then, and perhaps even planets and life before any stars as a result. But instead, the cosmos cooled beyond the point where fusion could continue, and it would be around 100 million years before stars could restart the process. The early universe. We can move a bit faster now as we enter more familiar territory. The universe continued to expand and cool, and by the T5 era, a few 100,000 years after the Big Bang, it had dropped to around the temperature of a typical star's surface. This is far below fusion temperatures, but still above the threshold where chemistry can occur. At this stage, atoms couldn't yet exist in a stable form. The universe was filled with free-floating nuclei and electrons. too hot for them to bind together. All matter was ionized, and this plasma was extremely effective at absorbing photons in the still dense and hot cosmos. Then a tipping point was reached. It became cool enough for electrons to begin binding with protons to form neutral hydrogen atoms, one proton and one electron, no electric charge. With few charged particles around to scatter them, photons could finally travel freely. This moment is known as recombination, and it gave birth to the cosmic microwave background radiation. The light released at that time was not in the microwave range. It was closer to visible light, with a spectrum resembling that of a glowing star. But over billions of years, cosmic expansion redshifted and cooled those photons into the faint microwave background we observe today. In future epochs, it will redshift more until it becomes cosmic radio background radiation. Anyway, at this point, chemistry can finally begin, but there's nothing to cook with. The only ingredients on the table are hydrogen, its isotope deuterium, a small smattering of lithium, and helium, which doesn't really participate in chemistry at all. So life is still completely off the menu. If the universe had expanded more slowly, there might have been time to form heavier elements in those early minutes, and perhaps life could have arisen in this era, but a slower expansion would also mean it would take longer to cool down enough for chemistry to even be possible, so we'd still be waiting either way. I mention this because in the late T6 and T7 eras, or its equivalent in other possible universes, the universe was about the temperature of bath water, and there had been more chemicals available than hydrogen. It likely would have involved a lot of it being oxygen, the third most abundant element, and nitrogen and carbon, so you could have gotten actual pockets made of mostly water with a mix of other chunks in them, in which life might have formed and thrived. And those would have clumped and cooled more slowly, thus you could have had life in this era before we had stars, who don't show up till late in the T7 and T8. We can hypothesize life emerging on comets in the T8 era as the first supernovae begin releasing heavier elements, but rocky planets won't form and cool enough to support life until well into the T9 era. No rocky planets with liquid surface oceans. From here, we are on more familiar ground. Galaxies form and merge, and rocky planets become increasingly common, though galaxies in this era are still quite active, with conditions that may be too chaotic for long-term, stable biospheres in which civilizations could emerge. As metallicity rises and calmer regions appear, planets become more habitable and life more plausible. It's possible that by the late T9 era, some intelligent civilizations may have already arisen, perhaps even loud or grabby civilizations, and with galaxies closer together then, some of them might have already settled entire superclusters before we even pop our heads up early in the T10 era. The Stelliferous Era, T10 to T14. We live in what may be the golden age of the cosmos. Stars shine, galaxies blaze, and the night sky is rich with light and structure. But like all good things, the Stelliferous Era, the age of starlight, has an expiration date. We are currently in the early part of T10, the first 4% in fact, and for now, the Milky Way remains a busy neighborhood. Stars are still being born in their billions, mostly small red dwarfs that were burned steadily for trillions of years. If the Stelliferous Era were looked at as a single day, the last star burning out at midnight, then we are only 12 seconds into this era. But the star formation rate is slowing. Gas clouds are thinning. The grand dance of galaxy mergers will one day reach its finale as our Milky Way collides with Andromeda, forming the future Milkdromeda galaxy, which is a horrible name, but we have a few billion years to think of a better one. And as this process plays out, the wider cosmos will begin to darken and drift apart. Galaxies that are not gravitationally bound to us are already vanishing over the cosmological horizon. Thanks to accelerating expansion of space, Hubble expansion will eventually leave us as the lone occupants of a vast starry island, Milkdromeda surrounded by billions of light years of silence. Civilization in that distant future might barely remember that other galaxies ever existed, unless they took the time to archive the sky while it was still full. As the T11 era begins, virtually every bit of the universe will consist of such merged galaxies, surrounded by empty nothingness for billions and billions of light years around. Just a few billion scattered stars left spread out and abandoned, and the ever more stretched out light from those other merged galaxy islands as they begin fleeing over the cosmological event horizon. Some of those galaxies might even host human colonies, or at least our distant descendants. After all, everything within a billion light years of us today might still be reachable given enough patience and proportion. And given the immense timelines involved, it's entirely possible that the majority of humanity, or whatever we may become, will end up living in those far-off island galaxies, not here in the familiar confines of Milkdromeda. In fact, with enough determination, we might even manage to drag a few of those galaxies back before they slip beyond the cosmic horizon. Those like the Council of Giants that only receding at a modest pace of 1 or 2% of light speed or less. So our galactic island might be a lot bigger and a lot less natural by then, as I doubt we will leave things for nature to have its way. Yet even if we did, within our galactic island the change continues. By the late T12, star formation, especially of large stars, will have dropped off heavily. The last large stars will have exploded in spectacular supernovae or quietly faded into white dwarfs. Only the dimmest red dwarfs, those little candlelights of the cosmos, will remain, burning with glacial slowness. These stars might last 1 trillion years or more, but their light is faint, and they're notoriously frugal with their energy. At this point, if there are still civilizations around, they'll need to be either extremely efficient or extremely ambitious. The days of casually scooping up hydrogen clouds to make new stars will be long gone. Matter will be locked into long-lived remnants, perhaps trickle-fed in those remnants like black holes to generate power, and the space between them will stretch even wider. Star systems will be like distant towns, separated by deserts the size of continents. Trade routes, possibly, but you'll want a good audiobook for the trip, maybe even the entire Library of Congress. There's also a question of whether civilizations in this era would even want stars anymore. Stars are gloriously inefficient compared to purpose-built power plants. In a planetary context, we use less than 1/1000th of the sun's light here on Earth. It's like burning a forest to keep your hands warm. Artificial fusion may be cleaner, or perhaps they opt to hoard matter to trickle into optimized stars, extracting helium and heavier elements as byproducts. Star lifting, star boosting, or even star smothering to extend their life could all be on the menu. And here's where things get poetic. A post-biological civilization running on vast computing substrates and basking in the glow of long-lived stars might view our time, the age of bright galaxies and youthful stars, as a kind of flashbulb moment, a brilliant but chaotic childhood full of noise and promise. Their era, though dimmer, would be one of control, quiet mastery, and deliberate thought, stretched over millions or billions of subjective years. But even this contemplative age must end. By T13, star formation will have dwindled to a trickle, and by T14, around 100 trillion years after the Big Bang, the last natural stars will have formed. The curtain will fall on the Stelliferous Era, the lights will go out, and the long night will begin. Yet not all is dark, not yet, for in the cooling embers of the universe, in the degenerate husks of dead stars, and the whispers of radiation, life may still flicker, but to survive, it will have to evolve, not just biologically, but philosophically, no longer basking in sunlight, but eking out energy in long twilight, one trickle at a time. Into the darkness, T15 to T67. But even those island galaxies, whether preserved, settled, or salvaged, are just temporary refuges in the grand sweep of cosmic time. The Stelliferous Era, the age of stars, will eventually come to an end, and when it does, we enter a new chapter, the Degenerate Era, beginning somewhere around T14 or T15, about 100 trillion to a quadrillion years after the Big Bang. By this time, star formation has all but ceased, but most remaining stars are long-lived red dwarfs putting out their last fuel, or white dwarfs slowly fading into cold black lumps. New stars no longer form naturally, not because hydrogen is gone, but because it's too spread out to collapse under gravity without interference. The night sky, once full of stars, now holds only cooling embers. And yet, it need not be a cosmic graveyard. Advanced civilizations may find ways to extend the stellar epoch, fueling old stars or even manufacturing new ones. They might consolidate resources, switching from solar power to artificial fusion or black hole engines. Indeed, if you live in the Degenerate Era, it likely means your civilization chose to do so, that you hunkered down in well-insulated habitats, tending your dwindling stockpiles, stretching every atom and erg of energy with careful, deliberate purpose. This is no longer the age of expansion, it is the age of endurance. Civilizations in this era may run slowly, sleeping between cycles of activity, or exist entirely as intermittent digital minds, flickering on and off across the cold eons. The stars no longer burn, but intelligence might still shine on. We can talk about what would still happen here: black holes swallowing remnants, or planets orbiting dead stars spiraling inward from gravitational decay, but in many cases there may be no one left to witness these events, or they may not happen at all, because advanced civilizations have already stepped in to shepherd their resources, choosing not to let things play out naturally. Perhaps they've even discovered workarounds for the conservation of energy or the increase of entropy. After all, they've had 1,000,000,000 times longer than our civilization has existed to solve these problems before the dark times even began. And yet, even if all known life has retreated or perished, the universe is vast. There may be regions never reached by intelligence before Hubble expansion carried them beyond contact, where life still has a chance to arise anew. Occasionally, some drifting cloud might reignite a dead star for a brief time, or two long-lost worlds could collide to form a slowly cooling remnant. A rogue planet might find itself caught in orbit around a black dwarf or brown dwarf, warmed by tidal forces. Two brown dwarfs might emerge to form a new dim star heating its former moons. These would not be long-lived or energetic enough for stable civilizations to form, but life, known for its tenacity, might still emerge. It is conceivable that both life and even intelligence could arise independently well into the T15 or even T20 eras. Beyond that, however, survival requires more than luck. It demands foresight, technology, and deliberate preservation, a will to shepherd life through the long, cold dark. Today we're talking about how civilization could have arisen far earlier in time than it did, and how it might endure unimaginably longer than the current age of the universe. But every civilization begins with a spark. Often it's one of industry, and when it comes to our future in space, that spark may be mining the moon for raw materials. Getting those materials into orbit might not be done with rockets though. That's why in this month's Nebula exclusive, Mass Drivers on the Moon, we explore how electromagnetic catapults, massive launch tracks on the lunar surface, could transform the moon into humanity's first great off-world freight hub, hurling millions of tons of rock into space to build habitats, power stations, and even megastructures that break the chains of scarcity. But civilization may also arise in strange and shadowed places. That's the focus of next month's Nebula exclusive, Dark Biospheres, where we explore how life might evolve on tightly locked planets, rogue worlds, or sunless voids far from any star, ecosystems that thrive in eternal night. And sometimes, civilization is born not from abundance or planning, but from chaos and desperation. That's the world of the Sojourn, Nebula's original sci-fi audio drama. It's a tense, character-driven story set in a hazardous star cluster, where fragile alliances and survival instincts shape every decision. If you're curious what humanity might become in the face of deep space adversity, it's a must-listen. I've been releasing bonus content on Nebula now for over 6 years, including monthly exclusive episodes for the last 3 years, and you can watch my monthly exclusive, Mass Drivers on the Moon, along with all my other exclusive videos, The Sojourn, and every episode of this show early and ad-free on Nebula. Sign up for just $36 a year, or get a lifetime membership for $300 and unlock everything forever. Head to go.nebula.tv/IsaacArthur and keep exploring the future with us. The Black Hole Era. By the time we enter the Black Hole Era, which stretches to around T100, the universe has become a silent graveyard of matter and motion. No stars shine, no new ones form. All the gas clouds have long since been consumed, dispersed, or hoarded by civilizations. Planets, moons, and stellar remnants have either fallen into black holes, collided, or been scooped up for megastructural projects now dormant or abandoned. What remains are the black holes themselves, massive, quiet engines slowly ticking through eternity. In this darkness we see an occasional rebirth, as black holes, depending on their size, finally begin dying from Hawking radiation, and those deaths, while brief explosions compared to their lifespans, can emit a life-giving amount of radiation for periods longer than the current age of the universe. Civilizations might farm these black holes for eons, living ultra-efficient, and ultra-cruel lifetimes of immense duration, both objectively and subjectively, as we discussed in the first episode of our Civilizations at the End of Time series, Black Hole Farming. This is often painted as the end, a long cooling sigh as entropy spreads to fill every corner of the cosmos. If intelligent life survives into this era, it may view black holes not as tombstones, but as lifeboats. These objects can be harvested for their energy, both from matter spiraling into their accretion disks and from their eventual evaporation. Indeed, civilizations in this age might construct vast habitats orbiting black holes, designed to slowly slip from their radiation like dew gathered in the desert. These would not be energetic places, but they could still sustain thought. More radically, some theories suggest intelligent beings could extend their existence almost indefinitely by slowing their thinking to match the trickle of available energy, a concept known as eternal intelligence. Others might stretch their lifespans by carefully staging black holes of varying sizes, triggering their evaporation in sequence across quintillions of years. In this scenario, a mind could outlive even the longest burning star. Still, even with perfect engineering, every resource eventually depletes, maintenance grows impossible, equipment fails, particles decay. This is a time where the universe is not just old, it is ancient beyond reckoning, and yet, for a mind operating at glacial speeds, T67 to T100 might feel like an ordinary span of life, not the twilight of existence, but just another season. And if no minds remain, the universe continues its slow descent into silence regardless. From here, we now enter the Dark Era, the long shadow that follows the final evaporation of black holes, an age when even gravity, the first and last architect of order, finally loses its grip. The Dark Era. After the last black hole evaporates, sometime after T100, or 10 to the 100 years, we enter what is often called the Dark Era. No stars remain, no galaxies. Even the black holes that ate whole galaxies are gone, their energy dribbled out over eons as Hawking radiation. What's left is a nearly perfect vacuum, filled only with low-energy photons, neutrinos, electrons, maybe protons, we don't know if they decay or not, and perhaps a few relic particles that escape decay. The universe is still expanding, still cooling, but with nothing left to cool. What was once a blazing sea of matter and light is now a frigid fog of almost nothing, and yet, the lights may not be entirely out. Given enough time, gravity does strange things, and in this age, one of the few active processes remaining is gravitational clumping and orbital decay. Planets and stellar remnants that survive the degenerate and black hole eras, possibly by floating freely in the immense extragalactic void after an ejection event, black dwarfs, neutron stars, and more, continue to drift, merge, and collide. Over timescales even longer than the evaporation of black holes, this process may lead to the formation of new objects, iron stars. Iron stars are hypothetical stellar remnants formed not through fusion, but by slow proton decay, neutron tunneling, and quantum transformations that eventually turn the material of ancient stellar husks into mostly iron, the most stable atomic nucleus. These are objects of extreme age, composed of the universe's last organized matter, and if any minds still exist in that far-flung epoch, may dwell around or within such structures. We explored this haunting possibility more deeply in our episode, Civilizations at the End of Time, Iron Stars. As for intelligence surviving this long, well, it's difficult to say. Perhaps civilizations have discovered loopholes in thermodynamics or unlocked power sources we cannot even begin to guess at. Vacuum energy, dark matter interactions, or exotic quantum effects. Perhaps they shepherd what little remains with meticulous care. They might run slowly or intermittently, sleeping between sparse pulses of activity, digital minds flickering on and off across cold eons. Or perhaps these events are unobserved because there's no one left to observe them, either because entropy finally won or because some civilizations chose to bow out before then, having decided they had lived long enough. And yet even here, there may still be light. In the unimaginable darkness, rare collisions between remnant objects might momentarily reignite fusion. A planet drifting in the void might brush too close to a brown dwarf, become tidally heated, and host life for a geological blink. Somewhere in an isolated patch of cosmic debris, a chance arrangement of chemicals might spark simple life anew. Most of those are dead ends, but a few might briefly bloom, perhaps even rising to intelligence, an echo of ancient cycles. But beyond this point, persistence requires planning. Intelligence can only survive here by choice, not chance, and the universe doesn't offer them an escape. Some may try to build one. Which brings us to our final chapter, not an epoch, but a question. Does the universe end, or does it begin again? Final fates, cycles, cracks, and cosmic cliffhangers. After 100 orders of magnitude in time have passed, from the first fractions of a second to a universe aged beyond imagining, it's tempting to assume that everything simply ends, that nothing can come after the Dark Era, but modern cosmology, like good science fiction, has plenty of twists left in store. One such twist is the idea that the universe might not be heading for a permanent heat death, but rather a reboot. According to physicist Roger Penrose's theory of conformal sacred cosmology, CCC, the cold, empty, infinitely expanded universe of the far future could resemble the high-energy, low-entropy conditions of the Big Bang, at least in a certain mathematical sense. If all mass and structure eventually decays or is radiated away, you're left with a massless, scale-invariant spacetime. From a conformal standpoint, that looks a lot like the beginning of a new universe. Time, in a sense, loses its scale and begins again. In Civilizations at the End of Time, Conformal Sacred Cosmology, and Ancient Ghost Universes, we explored how such a model might even leave behind imprints from previous aeons of the cosmos, perhaps in the form of subtle circular patterns in the cosmic microwave background, or as gravitational echoes from a time before our time. It is a radical idea, and not yet confirmed by observation, but if true, it would mean that everything we know is just one iteration in an eternal series of cosmic lifetimes. Of course, not every ending is so elegant. Instead of fading to black, the universe might end with a bang, or more precisely, a tear. If dark energy is not constant, but instead increases over time, it could drive a runaway expansion known as the Big Rip, a scenario in which galaxies, stars, planets, and eventually even atoms are pulled apart as spacetime itself is stretched to infinite size in finite time. We covered that nightmare and Civilization at the End of Time, the Big Rip, and needless to say, it is not a gentle conclusion. If the Big Rip is correct, then we might not even make it to the end of the T10 era, let alone the grander ages of T11, T20, or beyond. The universe could disintegrate in just a few tens of billions of years from now. And that's still not the only wild card. There's also the prospect of false vacuum decay, which in a quantum tunneling event caused the universe to abruptly shift to a lower energy state, redefining the very laws of physics in the process and destroying everything at the speed of light. That could happen next week or never, and there's really no way to see it coming. Comforting, right? Yet even in the face of these ultimate ends, civilization may not accept its fate. The same intelligence that tamed fire, split the atom, and mapped the stars might one day find ways to escape the fate of its cosmos by bending the rules or breaking them altogether. If wormholes, baby universes, or higher dimensions prove real and navigable, they may provide doorways to new timelines, new realities, or fresh canvases on which life can paint itself again. Or perhaps, at the end of all things, there is simply one last experiment to run, to find out whether intelligence can make even entropy yield. We have walked through the ages of everything, across the quantum flickers of the earliest seconds, past the blazing lives of stars and the rise of galaxies, into the cold eras when light fades, matter dies, and the universe seems to fall silent. We've seen how even time itself stretches and warps in scale, until a single second might hold a lifetime, or a trillion years might pass in a whisper. And through it all, one thread has persisted: the question of whether we, or anything like us, can last. In the grand cosmic calendar, humanity has barely ticked past the first moment, but we are here. We have opened our eyes to a universe 3.8 billion years old, and dared to imagine its future across another 100 orders of magnitude and beyond. We have contemplated surviving the death of stars, the decay of matter, the evaporation of black holes, and even the end of time itself. Civilization as we know it may be fleeting, but intelligence, consciousness, the will to understand and endure, Those are not defined by flesh or cities or suns. Those are patterns, and patterns, if cleverly preserved and fiercely pursued, might last longer than any star. Maybe we'll vanish without a trace, burning bright and briefly like a match in a windstorm. Or maybe we'll find a way to stretch that match's glow into a torch, then a beacon, then a civilization so vast and strange that even galaxies will seem quaint by comparison. Or maybe, like the universe itself, we will cycle, rise, fall, and rise again, 1 trillion times, until we finally learn how to make the clock run in reverse, or perhaps how to stop it entirely. We do not know what the future holds, but what a gift it is to ask. Because to even pose the question, can we endure, is to be alive in a way that early universe never was. It means we are part of the cosmos that knows it is a cosmos. And maybe, just maybe, that's enough to start tilting the scales of fate. Thank you for joining us today for Science and Futurism with Isaac Arthur. If you'd like to dive deeper into these questions, be sure to check out our Civilizations of the End of Time series, and of course the episodes we touched on today, black hole farming, iron stars, the Big Rip, and conformal cyclic cosmology. And if you're feeling timelessly inspired, consider liking, subscribing, and sharing this episode with others, wondering what might come after forever. Until next time, stay curious and keep your eyes on eternity. Thanks for watching, and have a great week.